Hello everyone, my name is Kyoung-Hee Kim. I am a professor of architecture and director of the Integrated Design Research Lab at UNC Charlotte. This presentation is an introduction to solar energy building integration. We'll briefly go over how solar energy technology has evolved and how it can be seamlessly integrated into buildings. For those interested in exploring this topic, here are two recommended books on BIPV that provide deeper technical and design perspectives. This slide and the following ones discuss the historical development of solar cell systems, move through key technological milestones, and finally discuss modern innovations and their impact. Two additional videos of design and engineering principles of solar facades continue to discuss why integrating them into our built environment is so important. The image on the right shows the first solar panels on New York City rooftop in 1884. Before the first building application, French scientist Edmond Becquerel discovered the photovoltaic effect and recorded how light generated voltage and current in a conductive material in 1839. In 1888, American inventor Charles Fritz fabricated first solar cells and filed the first patent was granted. Now let's jump to the mid-20th century. The photo on the right side shows the testing of a solar battery. In 1954, Bell Labs invented the first commercial solar cell with an output of 60 watt per square meter, which is equivalent to 6% efficiency. For reference, modern solar cells have about 20% solar efficiency. In addition to being integrated into buildings, solar cells were also used to power space applications. The Vanguard 1 satellite was the first satellite in history to be powered by solar cells in 1958. This application proved that solar technology could work even in space applications and led to further research. The world's energy crisis in the 1970s sparked investing heavily in solar research and development. Increasing investment and public awareness have made significant innovations in solar technology. Solar technology continued to evolve and gain traction in the real-world application in the late 20th century. With the introduction of new materials and technical advancement, solar panel efficiency reached 20%. These new materials included bifacial panels and perovskites. Bifacial solar panels, unlike traditional solar cells, capture light from both sides of the solar cells, which allows for greater sunlight collection. At the same time, solar systems were directly integrated into buildings. The University of Delaware's Solar One House was a landmark example as it became the first home fully powered by both photovoltaic panels and solar thermal collectors in the 1970s. The solar industry was scaling up during the 1980s. One of the first factories in Freiburg, Germany started mass production, leading to greater public accessibility and reduced cost. As the global adoption of solar technologies accelerates, different solar technologies are advancing their performance, cost, and aesthetics. For example, transparent solar panels provide the functionalities of conventional high-performance windows while simultaneously generating clean power. Printable solar cells can open up various geometric configurations beyond flat panel applications because they are flexible and less rigid. BIPV could turn high-rise buildings into vertical solar farms by seamlessly blending the solar cell with standard facade components, supporting the transition to decentralized, resilient energy buildings. Now let's look at the future solar acceleration. The green highlighted in the left side graph shows renewable energy share, which is projected to increase worldwide from 19% of total energy sources in 2020 to 38% by 2025. On the other hand, energy sources such as coal and nuclear power are projected to decline. When zooming into the renewable energy source sector, wind energy also shows a steady increase as a renewable electricity source. At the top right, solar and wind, highlighted in yellow and blue respectively, are projected to be the leading primary renewable energy. Solar power's share in the US is expected to grow from 16% in 2020 to 46% in 2050. That accounts for the most significant deployment growth. Their adoption would be further increased by technological advancements, supportive policies, and reinforcement from building codes. The widespread implementation of solar panels brings a new challenge about recycling once they reach the end of their life. The graph presents a recent study on solar energy capacity across different countries and the associated solar panel waste. It projects approximately 8 million tons of solar panel waste globally by 2030, soaring to around 78 million tons by 2050. The industry is now incorporating recycling practice as part of a circular economy and the carbon neutrality goal. The first step involves removing the aluminum frame and glass cover first before the solar cell are reclaimed. After this, the solar cell is either shredded or heated to extract silicon, plastics, and other metals. Current recycling facilities can recover approximately 90 to 95% of solar panels materials, which include glass, aluminum, silicon, and other precious metals. The recycled materials from solar panels help reduce the need for mining and extracting raw materials. This ensures that solar energy remains clean and circular economy throughout all stages of its life cycle. This video was supported by UNC Charlotte in collaboration with the US ASEAN Smart Cities Partnership. For further inquiries, please contact Kyoung-Hee Kim at UNC Charlotte. We appreciate your interest in advancing sustainable energy solutions through innovative BIPV integration.